Welcome, ladies and gentlemen, to my design presentation on the wing and aerofoil by yours truly, Inam Hussain. The design requirements of my aircraft wing. The chosen aircraft type that I designed and customized is the GA high wing prop, like the Cessna 182. This aircraft has a wing that is mounted above the fuselage. The wings on high wing aircraft tend to be flat with little dihedral or anhedral. I was allocated three pre-calculated values based on my SRN, which are rounded to the nearest integer. My ideal cruising speed of 80 meters per second, the all-up weight of the aircraft, which is 771 newtons, and my cruising altitude, which is 1,918 meters. Predicting the conditions of flight in cruise conditions. In the vertical direction, these forces are applied chiefly by the lift and weight. Vertically, the lift applied to the airfoil may be much greater than its weight, and there may also be some component of thrust or drag, or both also acting vertically, meaning that L has to be greater than W and vice versa. But these will be extremely small, that the effect of unbalanced forces is little to none. L has to approximate weight, which is a half rho v squared, multiplied by S and C by CL, and here and which is defined by these parameters. To work out the lift of my designed aircraft, I need to work out the air density at the cruise altitude, the planform area, and the coefficient of lift. To work out rho, I use the formula rho equals P over RT, which is defined here. Deciphering the values to predict the conditions of flight. The temperature in each atmospheric layer is approximated as a linear relation with altitude and a temperature gradient, known as the lapse rate, dt over dh, where t and h dashes are baseline values of the temperature and altitude at the base of the atmospheric band, based on this table. Since my cruising altitude is 1,918 meters, lower than 11,000, h dash is 0, c is minus 5.259, and dt over dh is minus 0.0065, and t dash is 288.15 Kelvin, and pressure is 103,325 pascals. Since dt over dh isn't 0, I can use this formula to work out T, which in turn helps me work out pressure, which means pressure is 80,296.8 pascals. Since T is 275.68 Kelvin and rho is 1.01486 kilograms per meters cubed, air density at cruise altitude, which is the air density at cruise altitude. Since air density and cruise speed is known, we can work out the dynamic pressure, Q bar, which means Q bar using this formula here. And so Q bar is 3,247.55 pascals. Predicting my coefficient of lift values and wing loading. The wing size dictates how much lift will need to be generated per unit area to match the weight of the aircraft. So choosing a small wing with high lift capability seems a sensible choice until it's insufficient with the characteristics of the ideal aircraft that I can modify it. But a higher wing loading will result in a higher stall speed, reducing the speed of the range of of the aircraft and leading to higher landing and takeoff speeds. But if wing loading is very low, then even if stall is no longer a problem, other factors such as bending moments and drag of a very large wing becomes troublesome. I was able to choose a wing loading of 43.25 kilograms over meters squared by benchmarking from the appendix benchmarking here from activity 2, and using my wing loading, I was able to work out my wing coefficient of lift, predicting the stall speed and planform area of my wing. By looking at this formula, it shows CL to be an inverse relation to velocity. So there's a limit on CL, as there will be a minimum speed at which the aircraft can't be flown any lower, otherwise not enough lift can be produced to match the weight. This limiting speed is corresponding with the maximum lift coefficient is the stall speed. Stall speed, maximum lift coefficient, which can be rearranged into each other. Again, by benchmarking, I was able to estimate my stall speed, which is roughly 25 meters per second, and my coefficient of lift value is a maximum coefficient of lift is 1.3378, and my planform area is 1.82. And by substituting these parameters into the lift equation, the value of lift is 771 newtons, which balances the weight of the aircraft. Picking a baseline airfoil. By benchmarking again, I was able to work out my aspect ratio as 8, which helped me work out these two values, ideal lift coefficient and max lift coefficient, which helps me pick my baseline airfoil, which is NACA 1412, and I can modify it in XFLR5. The pre-analysis of the airfoil. Before I can do analysis of my airfoil in my XFLR5 program, I need to work out the Reynolds number, which is defined by the dynamic viscosity, and it is defined by the characteristic, the dynamic viscosity, the characteristic length for L, which is B, my cruise speed, which is 80 meters per second, and my air density, and my this is a B for L. B is my wingspan of my aircraft. The Mach number of my aircraft at cruising altitude is 0.24, but since this is less than 0.3, it's subsonic. That means I can assume compressibility effects. So M can be 0. Here is my baseline airfoil of the NACA 1412. This is its successor through inverse design by modifying it, and this is my my flapped aerofoil, my prototype aerofoil of my 3D prototype, which is printed out, 3D printing. Analysis of the three aerofoils. In the polar chart on the right, the coefficient of lift versus angle of attack implies that its ideal lift coefficient is 0.112 and 12 degrees is angle of attack, where stalling occurs when CL equals max for the baseline airfoil, which is red. And its DCL over D alpha is 0.08669, which forms a baseline of the other airfoils. By modifying this, my inverse design blue airfoil, I was able to dictate that increase my CL max, which is 1.42, and adding a flap, it greatly raises the CL max, which is 1.67. This meets the design requirements of max lift coefficient, but it isn't the perfect one for the cruise. It has a max coefficient of moment that's greater than minus 0.1. Lower at 0 angle of attack, and the CL versus CD, it produces a greater ideal lift coefficient, 0.7, at the lowest coefficient of drag. So the blue airfoil is the best one. This one here. Here is my initial wing design parameters for the wing design. These are my first wings. First two wings. This is the one with no dihedral, and this is the one with dihedral. And it's based on these parameters here, which I imported into XFLR5. These are my analysis for XFLR5. The wing analysis on the first wing. By looking at the CL versus alpha, it is clear that the wing stalls at 18 degrees, and that by looking at the CL versus CD, the lift coefficient versus coefficient of drag is very low at CL equals 0.0076 at 0.029 right here. So there's not a great deal of a drag at the ideal lift coefficient. At about 1 degrees, the CL reaches a value of 0.13, which would enable the lift force of the aircraft to balance its weight, which is 771 newtons. The CL over CD is at its highest when alpha equals approximately 5 degrees. So at this angle, the aircraft can soar or glide for longer, achieving best cruise conditions. This is the wing analysis of my second wing with dihedral. This one was without dihedral. By looking at the CL versus alpha, it is clear that the wing soars at 18 degrees, and that by looking at the CL versus CD, the coefficient of lift versus coefficient of drag, it's very low at 0, like before. So there's not a great, and at about 1.2 degrees, the CL value reaches of angle of attack, the CL value reaches 0.13, which would enable the lift force of the aircraft to balance its weight of 771 newtons. The CL over CD is at its height when alpha is approximately 5 degrees. So at this angle, the aircraft can soar or glide for longer, achieving best cruise conditions at this angle of 5 degrees. Taking everything into account, the blue airfoil from inverse design was a great foundation of the wing. It has the lowest CL value, which is 0.016 at the lowest drag, so it can fly comfortably at cruise, requiring less lift to remain there. It is more stable than the other airfoils, so it does not reach the maximum lift coefficient. It has the highest stall angle of 15 degrees and can soar, and it can soar for long or glide for longer. According to the CL versus CD polar graphs on the wing, the lowest CL over CD are higher than the airfoil by in the 0.02 margin, and so its geometry needs to be modified. And its CM of both wings are much lower than the chosen airfoil, meaning that crews the aircraft will pitch down more, requiring a larger tail, which would produce more drag. So more modifications and testing is needed for it to be improved. Thank you for listening, and I hope you've enjoyed my presentation and my 3D printed airfoil for the prototype.